Hello, this is Chris again. I'm just going to continue on the lines of the binding energy that we talked about a little earlier and then much earlier than that. So this is just kind of a real quick recap that, look, when we wanted to calculate the binding energy of electron in a hydrogen atom, the proper formula that we would use, of course all this falls out of the Schrödinger equation, but the proper formula we use is -1 over n squared times the mass multiplied by the charge on the electron to the 4th power. I believe on the second video I'd inadvertently said e cubed, and it is in fact e to the 4th power, so I apologize if there's any confusion there. That divided by 8 epsilon naught squared, and the product of that with Planck's constant h squared. And we'd said, look, all of this is actually a constant. It doesn't change, so we can go ahead and we can make this the Rydberg constant, RH, and of course a -1 in front of that, or just negative RH, negative Rydberg constant over n squared, n being the principal or primary quantum number, the primary energy level. And then I said, well, that's great if I have 1 proton in the nucleus and then 1 electron in a cloud of probability density around that, a hydrogen atom. That's great. It works great at explaining that binding energy, but what happens if I have, say, helium with 2 protons in the nucleus, and I go ahead and I ionize one of the electrons in helium? So I have, say, helium plus, which is 2 protons and an electron instead of 2 protons and 2 electrons, like we'd find helium in nature. Well, clearly I have an additional charge, additional positive charge in the nucleus, and I have to account for that. And what we do is, the additional charge, it becomes what we call Z. So then we have to plug that additional charge into kind of a modified formula the first, and just put in -Z squared. In this case of helium, Z would be 2. Because I have 2 protons, I'd throw 2 in there. 2 squared times the Rydberg constant, a -2 squared, multiplied by the Rydberg constant divided by n squared. If this is say a helium atom or a helium ion in its ground state, n would equal 1. If it was in the first excited state, n would equal 2. Second excited state, n would equal 3, so on and so forth. I could do the same thing with, say, a lithium that has 3 protons, and it had an electron, so it'd actually be lithium plus 2, because it should have 3 electrons. I go ahead and take 2 electrons off, I only have 1 left. However, we know that a lot of the atoms that we talk about are not single electron atoms, and we need to find a way of explaining that. Or even before that, can we explain multi-electron atoms with this formula or this formula? Well, let's just go ahead and do a Gedanken experiment, a little thought experiment, and kind of think it through, and then I'll tell you what experimentation tells us. So let's just go ahead and let me give you a situation, and we'll keep it easy. What I'll do is I'll give you lithium. Okay, lithium has an atomic number of 3, so what does that mean? Well, that means that I have 3 protons, positive charge, +1 elementary charge in the nucleus. Now, we know that lithium is normally going to, in nature, is going to be what? Well, it's going to be a 3-electron atom. So what does that tell me? Well, it tells me that I have my ground state, which is a 1s orbital, is going to have 2 electrons in it, right? So my 1s orbital is going to have 2. We call that 1s2. And now this just becomes an electron configuration experiment here. We know that I can only fit 2 electrons in an orbital, and this 1s, n equals 1. Okay, and we know that at the ground state, I can only have 1s orbital. I can only fit 2 electrons in there, and it's full. Well, I have 3 electrons, so what happens? Well, I move to n equals 2. Okay, so the second, You know, my principal quantum number now is 2. And what do I have? Well, I have another s orbital. I have, instead of a 1s orbital, I now have a 2s orbital. And instead of 2s2, I just say 2s1 because I only have one electron. And if I had another electron, of course, that would be 2s2, and my s orbital is filled, but in the second energy level, I have a little more space, if you will, and then I have p orbitals that I can fill up. But let's just go ahead and keep it simple and say, look, this is what we have. We have 1s2, 2s1. So then the question is, what is the binding energy of this electron here in the 2s1 configuration? Okay, so N equals 2, right? The principal quantum number that identifies that atom's 2, right? L equals, well, 0 because it's an s orbital. M sub L, again, equals 0 because there is no angular dependence, all radial dependence. I'm talking about the quantum numbers. Again, it's M sub L always be 0 in an s orbital. And then M sub s, the spin, we can just say it's, you know, positive 1/2. It's really not relevant. So these are the quantum numbers, the 4 quantum numbers for that electron. Well, that's nice, but what's the binding energy of that electron? Well, what would my formula predict? Well, my formula would predict that all I need to do is I need to go, you know what? I just, you know, this is a multi-proton atom, so I want to use the second formula. So I could go, look, you know, negative z, which in this case is going to be 3, right? So negative 3 squared times r sub h divided by what's n? Well, n is 2, right? Because that electron is in the second energy level. 2 squared. And then I get a value, x. And it's not really that important to know what that value is. What that value does is it predicts, hey, that's what we get. Well, what do we get when we experiment with lithium? And I go ahead and I actually try to ionize that electron. Well, what we find out is there's actually less binding energy. So the binding energy is lower than expected. Well, this is a problem. Is this telling us that maybe quantum mechanics is wrong? That maybe we have a flawed formula here? You know, maybe everything that we know about nature is fundamentally flawed, and that in fact quantum mechanics doesn't describe nature? Maybe. Or maybe this formula still works, but maybe there's something else going on that we haven't accounted for. And I think you might kind of have an idea of what that is. So let's just go ahead and draw this. If you remember back to our discussion on the Coulomb's law, the electrical interaction, if I have a positive charge and a negative charge, I can use Coulomb's law. And basically what it tells me is, hey, there's an attraction. But what if I have two of the same charge? Maybe a negative charge and a negative charge, and I put them close to each other. They're not attractive, but they are repulsive. There is a repulsion there. Well, that same thing occurs in multi-electron atoms. So let's take that lithium again with its 3 protons. And what I get here is I have 2 electrons in the 1s orbital, the 1s2, and then I have that third electron in the s orbital, the 2s1 configuration. Well, what have we got here is we've got electrons in close proximity to one another. So what do you think might be going on here? Well, there's electron repulsion, right? These electrons are kind of repelling each other because of the Coulombic interaction. So I have 2 things going on. I have the electrons are attracted to the positive charge in the nucleus, but as I get these electrons closer to each other, there's a repulsion. And that repulsion actually makes what this electron out here feels, the binding energy, it actually feels less binding energy because of the repulsion. And that concept of the repulsion causing the binding energy to be lower than we would think is something known as shielding. It's not really shielding, but a way that you can look at it is these inner electrons, or what we call the core electrons, are shielding the outer electrons, or what we call the valence electrons. Remember, valence electrons live in the outer shell of the atom. So these inner electrons, because of the repulsion, in essence, shield these outer electrons, and these outer electrons do not feel the full positive free charge of the nucleus, basically because they're getting close to one another and they're feeling some repulsion there. So that actually explains perfectly what we see in experiments. So we kind of have to modify the binding energies a little bit when we take into consideration multi-electron atoms. All right, guys, hopefully you found that interesting and helpful. Thanks again.